Hello students of class 10, those who have advanced mathematics. Page number 64, diagrammatic representation of complex numbers in a plane. We have already discussed that every complex number z is equals to x plus iy can be represented by an ordered pair xy of real numbers. Also, we know that if the real scales are chosen on two mutually perpendicular axes, that is the x-axis and the y-axis respectively, then we can locate any point in the plane determined by these lines by the ordered pair of real numbers xy called rectangular coordinates of the point. Now, since a complex number x plus iy can be considered as an ordered pair x, y of real numbers, we can represent such numbers by points on xy plane. Thus, we have seen that to each complex number there corresponds one and only one point in the plane, and conversely to each point in the plane there corresponds one and only one complex number. It is because of this reason that we refer to complex number z as the point z or pz. The plane having a complex number assigned to each of its points is called the complex plane. This plane is also sometimes called as Argand plane in the honor of Jean Robert Argand. So the complex number minus 4 minus 3i, which corresponds to the ordered pair minus 4 minus 3, is represented in the Argand plane by the point Q. Okay. The point M x, 0 on the x-axis represents the complex number x is equals to x plus I. This is okay. X plus I dot 0, which is a real number. The point N 0y on the y-axis represents the number iy is equals to 0 plus iy, which is a purely imaginary number. So we have seen that every point on the x-axis represents a real number and every point on the y-axis represents a pure imaginary number. Therefore, sometimes we refer to the x-axis as real axis and the y-axis as imaginary axis. The representation of a complex number on a complex plane is called a Argand diagram. It is already stated in 2.2.1 that the set of complex numbers is represented by C is equals to AB, A belongs to R, B belongs to R. Since A plus I dot 0 it is equals to A, 0 is a point on the real axis, and this is 0 plus IB, which is 0B, is a point on the imaginary axis. Therefore, the real axis and the imaginary axis are respectively represented by real axis is equals to A, 0, A belongs to R, and imaginary axis as 0, B, such that B belongs to R. Also, this A, 0 where A belongs to R is a proper subset of AB, such that AB belongs to R, and this is 0, B such that B belongs to R is a proper subset of AB such that AB belongs to R. So this is the set AB such that AB belongs to R. This is the set of all complex numbers which is represented by C. This is the set of all complex numbers. Okay, and this is on the real axis. Okay, the points on the real axis, since you see in here, okay, the points on the real axis, those points, the coordinates of those points will be in the form A, 0, where A will be a real number, and on the imaginary axis the coordinates of the point will be 0, B, where B will be also a real number, but this is on the imaginary axis, the points on the imaginary axis it will take the form of 0 comma b. Okay, and as we know that a complex number, it has two parts, one real part and another imaginary part. So the imaginary part will be denoted by the y-axis or the imaginary axis, and the real part, it will be denoted by the x-axis or the real axis. Understand? And all of this, the points on the real axis, those will be real numbers, and those all real numbers, I know that they are proper subset of complex numbers. Next, the points on the imaginary axis, they will take the form of this 0 comma b. Okay, b belongs to r, and all the points on the imaginary axis, they will be also a proper subset of the set of complex numbers. Okay, so from here we learned that a complex number can be represented by the ordered pair, this x comma y. We have already learned it. Understand? That means this ordered pair x comma y, that means what? It represents a point. Yes, it represents a point on the complex plane. Yes, it represents a point xy. It represents a point on the complex plane, or we can call it the argon plane. Okay, and we also know that if the real scales are chosen on two mutually perpendicular axes, x-axis and y-axis, then we can locate any point in the plane determined by these lines by the ordered pair of real numbers xy, called the rectangular coordinates of the point. Yes, so this point, for example, first of all, we know that a complex number, which is x plus iy, I can write it as ordered pair x comma y. Okay, and this x comma y, this ordered pair, yes, or you can call it this coordinate point. Okay, it is a point on the complex plane, or this complex plane we can call it the argon plane. For example, like this x comma y, this is a point. Okay, so we can locate any point in the plane determined by these lines. If we draw x-axis and y-axis on the argon plane, okay, and after that we can locate any point. Okay, with the help of this x-axis and y-axis, we can locate any point on the argon plane. So in here, since a complex number can be considered as an ordered pair xy of real numbers, we can represent such points by points on the xy plane. Thus we have seen that to each complex number there corresponds one and only one point in the plane, and conversely to each point in the plane there corresponds one and only one complex number. Okay, it is because of this reason that we refer to the complex number z as the point z or pz. The plane having a complex number assigned to each of its point is called the complex plane. Okay, the plane having a complex number assigned to each of its points is called the complex plane. This plane is also sometimes called the argon plane. Okay, so you see the complex number minus 4 minus 3i, which corresponds to the ordered pair minus 4 minus 3, is represented in the argon plane by the point q. This point q, this complex number minus 4 minus 3i, it is represented in the argon plane by the point q. Understand? The point mx comma 0, this point, you see mx comma 0, this point, it is on the x-axis, and this represents the complex number x plus I dot 0. And similarly the point you see 0 comma y, this represents the complex number 0 plus I y, which is a pure imaginary number. Okay, I y, this is a pure imaginary number. So we have seen that every point on the x-axis represents a real number. Every point on the x-axis represents a real number, and every point on the y-axis, represents a pure imaginary number. So therefore, we sometimes refer the x-axis as the real axis and the y-axis as the imaginary axis. Okay. So since a plus I dot 0, or I can write it as a comma 0, is a point on the real axis, and 0 plus ib, which is equals to 0b, is a point on the imaginary axis. Therefore, the real axis and the imaginary axis are respectively represented by real axis is equals to, I can write it as a comma 0, such that a belongs to R, and imaginary axis such that 0 comma b, such that b belongs to R. Okay, and you see, for example, this is a point. Let's say a comma 0, such that a belongs to R. This is a point on the x-axis, and this will be a proper subset of the set of complex numbers. And the point on the imaginary axis, this will be a proper subset of the set of complex number. Okay. Next, modulus of complex number and its properties. Let us take the complex number z is equals to x plus iy. As discussed earlier, this number can be considered as the point pz or p x comma y in the argand plane. PM perpendicular OX and OP is joined. Okay, PM perpendicular. We have taken a complex number x plus iy, and I know that this can be written as this complex number can be considered as a point. Yes, because I can write it as an ordered pair. I can write it as an ordered pair x comma y. So I can consider this complex number as a point. I can write it as pz or p x comma y in the argand plane. This is the point. Okay, I can write it as p x plus iy or p x comma y. Okay, this is the point. So PM perpendicular to OX, okay, and OP is joined. Okay, so OM will be x, because the complex number is x plus iy. This is x plus iy. So this will be x, okay, and this will be y. Okay, the x-axis represent the real part and the y-axis represent the imaginary part. So this will be x and this will be y. Understand? And the distance, this OP, the distance, if I use Pythagoras theorem, I will get OP square is equals to PM square plus OP square. Ultimately, I will get OP square is equals to PM square plus OM square. So OP will be is equals to root over PM square plus OM square. So is equals to, this will be x square plus y square. So OP is equals to this distance. This distance, it is root over x square plus y square. The distance of the point P, the distance of the point, this distance OP, the distance of the point P from the origin, which is OP, is called the modulus of the complex number. This distance, it is called what? It is called the modulus of the complex number. So if z is equals to x plus iy, modulus of z, which is the distance of this point from the origin, understand, which is the distance of this point from the origin, it is equals to root over x square plus y square. Understand? It is denoted by R or modulus z. I can write like that also. R is equals to modulus z is equals to root over x square plus y square. Okay, which is a non-negative real number. Okay, this distance, it is a non-negative real number. So now in here you see example Find the modulus of the following numbers. Find the modulus of the following numbers. Z is equals to 2 minus 7i. So in your solution, Z is equals to 2 minus 7i. This one I can write it as Z is equals to 2 plus I into minus 7, A plus IB form. Okay. So modulus Z, it is equals to root over x square plus y square. It becomes 2 square plus minus 7 the whole square, root over 4 plus 49 root over 53. This is the answer. Okay. Next again it is given number 2. Z is equals to 1 plus 2i by 1 minus I the whole square minus 2i. So this is equals to 1 plus 2i by 1 minus 1 square plus I square minus 2i by 1 plus twice I by 1 minus 1 minus 1 minus 2i 1 plus 2i by 1 minus 1 plus 1 plus 2i minus 2i. So this becomes 1 plus 2i by 1 plus 2i minus 2i. So this is 1 minus 2i. So therefore Z is equals to 1 plus 2i. Yes, I can write this in this form. So therefore modulus Z root over 1 square plus minus 2 the whole square is equals to root over 1 plus 4 is equals to root over 5. This is the answer. Okay. Next, question number 3. You see, I have to, first of all, remember I have to bring it in the form of A plus IB form. Then only I can find the modulus. Number 3, Z is equals to 1 plus 3i 2 minus I. So this is equals to 2 minus I plus 3i 2 minus I plus 6i plus 3i, sorry, this is minus 3i square. So this is 2 plus 5i plus 3, 5 plus 5i. So modulus Z, this is equals to root over 5 square plus 5 square is equals to root over 25 plus 25 is equals to root over 50. Okay. Now this one root over 50 means 52, 25, 5, 5, 5, 1. So is equals to 5 root 2. This is modulus Z. Okay. Now next you see properties of modulus of complex number. Okay. Properties of modulus of a complex number. So property number 1, the modulus of conjugate of a complex number is equal to the modulus of the complex number. That is, if Z is a complex number, then modulus Z is equals to modulus of Z conjugate. Understand? The modulus of the conjugate of a complex number is equals to the modulus of the complex number. The modulus of the conjugate of the complex number, this is equals to modulus of the complex number. Okay. So then let Z is equals to x plus iy be a complex number, then Z modulus will be x minus iy, which is I can write as x plus I into minus y. So Z modulus will be root over x square plus y square, and Z bar modulus will be x square plus minus y the whole square, which is also equals to root over x square plus y square. So therefore Z modulus is equal to Z bar modulus. Next again you see the modulus of a complex number is equal to the modulus of its additive inverse. That is Z modulus is equals to negative Z modulus. Okay, this is they have showed. The product of a complex number which is with its conjugate is equal to the square of the modulus of the complex number. That is, for a complex number z, z into z bar, it is equals to modulus z the whole square. Modulus z the whole square. Okay. So next it is the modulus of the product of two complex number is equal to the product of their moduli. So you see, modulus z1 into z2, it is equals to modulus z1 into modulus z2. Okay. Next it is, for two complex numbers z1 and z2 where z2 not equals to 0, modulus z1 by z2, it is equals to modulus z1 by modulus z2. Next again, if z not equals to 0 is a complex number, then z inverse, it is equals to modulus z by, z inverse, it is equal to z bar by modulus z square. Okay. The modulus of the sum of two complex number can never be greater than the sum of their moduli. So modulus z plus z2, it is less than equals to modulus z1 plus modulus z2. The modulus of the difference of two complex number can never be smaller than the difference of their moduli. That is, modulus z1 minus z2, it is greater than equals to modulus z1 minus modulus z2. Next again it is, you see, also we have modulus z1 minus z2, it is less than equals to modulus z1 plus modulus z2. Okay. This is, you see, modulus z1 minus z2 greater than equal to z1 minus modulus z1 minus modulus z2, and in here modulus z1 minus z2, it is less than equals to modulus z1 plus modulus z2. Next, for two complex numbers z1 and z2, this is, you see, modulus z1 plus z2 square plus modulus z1 minus z2 square, it is equals to 2 into bracket modulus z1 square plus modulus z2 square. This is, they have proved it. Okay. So next it is our worked out examples. Prove that modulus z equals to 0 if and only if z equals to 0. And next is modulus z is greater than equals to 0. So solution, they have taken, let z is equals to a plus ib. Then modulus z, it will be is equals to root over a square plus b square. Now if modulus z1 equals to 0, then this will be equals to 0. Then a square plus b square will be equals to 0. Since the sum of two positive numbers cannot be 0, so a equals to 0 and b equals to 0. Therefore, z is equals to a plus ib is equals to 0 plus I dot 0 is equals to 0. Conversely, let z is equals to 0, then a plus ib is equals to 0, a equals to 0 and b is equals to 0 by property. So modulus z, it is equals to root over a square plus b square is equals to root over 0 square plus 0 square is equals to 0. Okay. Find the modulus of each of the following numbers. So modulus 4 minus 3i. So in here, you see, I can take, let z is equals to 4 minus 3i. So modulus of z, it will be is equals to 4 square plus minus 3 the whole square is equals to root over 16 plus 9 is equals to root over 25 is equals to 5. So modulus of z, it is equals to 5. Next you see number b, minus 6 plus 8i. So again solution, I will take, let z is equals to minus 6 plus 8i. So modulus z, it will be minus 6 the whole square plus 8 square. So this is 36 plus 64. So this is root over 100, which is equals to 10. Understand? Next again, number C, 3 plus 4i, 5 plus 12i. So let z is equals to 3 plus 4i, 5 plus 12i. So this becomes 3, 5 plus 12i plus 4i, 5 plus 12i. So 15 plus 36i plus this is 5 plus, okay, 5 plus 3, 5 plus 12i plus 4i, 5 plus 12i, 15 plus 36i plus 20i plus 48i square. So 15 plus, this is 56i minus 48. So 48 minus 15, 3 and 3 minus 33 plus 56 I. So therefore modulus z is equals to root over minus 33 square plus 56 the whole square. This one you find it by yourself. Okay, next again you see number D. Number D 3 plus 4i by 5 plus 12i there. So let z is equals to 3 plus 4i by 5 plus 12i. So this I can do 3 plus 4i into 5 minus 12i by 5 plus 12i into 5 minus 12i. So this it will become 3, 5 minus 12i plus 4i, 5 minus 12i. Okay, so 3 into 5 minus 12i plus 4i into 5 minus 12i. By this it will become 5 square minus 12i the whole square. So this is 15 minus 36i plus 20i minus 48i square by 25 minus 144i square. So this is 15 minus 36 minus 20, you will get minus 16i plus 48 by 25 plus 144. So 48 plus 15, you will get 9, 10, 11, 12, 13, 13, 5, 6. 63 plus 63 minus 16i by this one you will get 169 you will get. Okay, 169 you will get. So this is equals to, you can write as 63 by 169 minus 16i by 169. So therefore z modulus it will become is equals to so question number D. Question number D, you see, first of all I will take let z is equals to 3 plus 4i by 5 plus 12i. So modulus z it will be is equals to modulus 3 plus 4i by 5 plus 12i. Okay, so we know that from property modulus a by b, this is equals to modulus a by modulus b. So this equals to, it becomes modulus 3 plus 4i by modulus 5 plus 12i. Understand? Now this modulus it will become root over 3 square plus 4 square by this modulus it becomes root over 5 square plus 12 square. So this is equals to 9 plus 16 by, and this becomes equals to 25 plus 144. So this is equals to, you will get 20 root over 25 by root over 169, which is equals to 5 by 13. This is the answer. Understand? So next again you see number E. Number E, 1 minus I to the power minus 2 plus 1 plus I to the power minus 2. So solution, let z is equals to 1 minus I to the power minus 2 plus 1 plus I to the power minus 2. So this, it will become 1 by 1 plus I to the power 2 plus 1 minus I to the power 2, 1 plus I to the power 2. So this one I will get 1 plus I square minus twice I plus 1 plus I square plus twice I. So this one, it will become 1 minus 1 minus twice I plus 1 minus 1 plus twice I. 1 minus twice I plus 1 plus twice I. So this, ultimately I will get minus 1 by twice I plus 1 by twice I. This is equals to 0 I will get. Understand? So therefore modulus z, it will be is equals to root over this one 0, which is equals to, I can write 0 plus I dot 0, root over 0 square plus 0 square. This is equals to 0 I will get. Okay. So next one, you see number f. Okay, number f, 1 by 1 plus I. So in your solution, let z is equals to 1 by 1 plus I. 1 minus I, 1 plus I into 1 minus I can do. Yes. So this is 1 minus I by 1 square minus I square. So this becomes 1 minus I by 1 plus 1. So this becomes 1 minus I by 2. 1 by 2 minus I by 2. So therefore modulus of z, this will be is equals to root over 1 by 2 the whole square plus minus 1 by 2 the whole square, root over 1 by 4 plus 1 by 4, root over 2 by 4. This is root over 1 by 2, which will be 1 by root 2. This will be our answer. Understand? Let's check the back answer. Exercise 2.3 type 2 number F. Exercise 2.3 type 2 number F. You see 1 by root 2. Understand? Now next one you see it is number G. Number G, 1 minus I, 1 plus I. So this one you can do in this way. Let z is equals to 1 minus I by 1 plus I. So modulus z, this will be modulus 1 minus I by 1 plus I. This will become modulus 1 minus I by modulus 1 plus I. So this will be root over 1 square plus 1 square by root over this is 1 modulus 1 plus I, root over 1 square plus 1 square. 1 square plus, this will be 1 square plus minus 1 the whole square. Okay, 1 minus I there. So minus I the whole square. So this will be root over 2 and this will be root over 2. So ultimately it will be 1. Okay, ultimately it will be 1. Next again, number H, you see number H, it is given 1 plus I into 2 plus I by 3 plus I. So solution, in here I can write let z is equals to 1 plus I into 2 plus I by 3 plus I. So okay, so modulus z, it will be is equals to modulus 1 plus I into 2 plus I by 3 plus I. So by property I can write this on modulus 1 plus I, 2 plus I by modulus 3 plus I. This one again I can break modulus 1 plus I into modulus 2 plus I by modulus 3 plus I. So this ultimately becomes root over 1 square plus 1 square into root over 2 square plus 1 square by root over 3 square plus 1 square. This is ultimately I will get root over 2 into root over 5 by root over 10. Okay, so this one root over 2 dot root over 5. This one I can write as root 2 into root 5. Yes, root 10 I can write root 2 into root 5. So ultimately is equals to I will get 1 here. Okay, I will get 1. Next again you see number I. So 1 minus I, 1 minus twice I by 1 minus 3I. So let Z is equals to 1 minus I, 1 minus twice I, 1 minus 3I. So modulus Z, it will be is equals to modulus 1 minus I, 1 minus twice I, 1 minus 3I. So this becomes modulus 1 minus I, 1 minus twice I, modulus by modulus 1 minus 3I. So this again become modulus 1 minus I into modulus 1 minus twice I by modulus 1 minus 3I. So this becomes root over 1 square plus minus 1 the whole square into this becomes 1 square plus minus 2 the whole square by this becomes root over 1 square plus minus 3 the whole square. So ultimately you will get root over this one you will get root over 2 into root over 4 5 by this one again you will get root over 1 plus 9 again 10 only you will get. So this one you will get root 2 dot root 5 by root 2 dot root 5. So ultimately 1 only you will get the answer. Okay. Question number 5. In here it is saying that if Z is equals to x plus iy and Z minus 5i by Z plus 5i is equals to 1, then prove that y is equals to 0. Solution. So in here you see Z is equals to this given, I have to prove Z, and this is equals to 1 given, I have to prove that y is equals to 0. So therefore I will start Z minus 5i by Z plus 5i, this is equals to 1. So modulus there, so this becomes Z minus 5i by modulus Z plus 5i, this is equals to 1. Z value it is given as x plus iy minus 5i by x plus iy plus 5i, this is equals to 1. So if I send this one this side, I will get x plus iy minus 5i is equals to modulus x plus iy plus 5i. Okay. So this one if I take x I common, I will get y minus 5 is equals to x plus I, y plus 5. So now this becomes root over x square plus y minus 5 the whole square is equals to root over x square plus y plus 5 the whole square. Okay. So now what I will do, squaring both sides, root over x square plus y minus 5 the whole square is equals to root over x square plus y plus 5 the whole square. So if I do squaring both side here, if I do squaring both side, I will get x square plus y minus 5 the whole square is equals to x square plus y plus 5 the whole square. So now in here you see x square it cancels out. This I will get y square plus 5 square minus 2 dot y dot 5 is equals to y square plus 5 square plus 2 dot y dot 5. So again from here you see y square, 5 square I can cut. I will get 2 y dot 5 is equals to 2y, this I will get. So ultimately minus 10y is equals to 10y I will get here. So this is minus 10y is equals to 0, minus 10 common, instead of taking minus I can, this is minus 20y is equals to 0, so y is equals to 0 by minus 20, so y is equals to 0 I will get. This is our solved. Okay. Question number 6, number A. If z is equals to x plus iy and modulus 2z plus 1 is equals to modulus z plus 2, then show that x square plus y square is equals to 1. So in here it is given if z is equals to x plus iy and modulus 2z plus 1 is equals to modulus z plus 2, then show that x square plus y square this is equals to 1. Now solution. So this is our given 2z plus 1 is equals to z plus 2. So z value it is given 2x plus iy plus 1 is equals to x plus iy plus 2. So this becomes 2x plus 2iy plus 1 is equals to x plus 2 plus iy. So this becomes in here, this one you can write as 2x plus 1 plus 2iy is equals to x plus 2 plus iy. So this thing it becomes, you see, this one is the real part, this one is the real part. So this thing becomes root over 2x plus 1 the whole square plus 2y the whole square is equals to root over x plus 2 the whole square plus y square. So this thing it becomes 2x the whole square plus 1 square 2.2x dot 1 plus 4y square is equals to root over x square plus 2 square 2x dot 2 plus y square. So this is root over 4x square plus 1 plus 4x plus 4y square is equals to root over x square plus 4 plus 4x plus y square. So now squaring both sides, I will get 4x square plus 1 plus 4x plus 4y square is equal to x square plus 4 plus 4x plus y square. Okay, so in here you see 4x it cancels out. Let us bring all of this to one side. 4x square minus x square plus 1 minus 4 plus 4y square minus y square is equals to 0. So now this is I will get. So this I will get 3x square minus 3 plus 3y square is equals to 0. So 3x square plus 3 in here let us take 3 common. So 3 common, x square minus 1 plus y square is equals to 0. So x square plus y square minus 1 is equals to 0. So x square plus y square is equals to 1. This is our proved. Understand? This one you can write as squaring both sides. Okay, squaring both sides you will get this. Next we will go to 6 number B. Okay, next we will go to number 6 number B. So number 6 number B telling that if W is equals to A plus IB and W plus 6 is equals to 2W plus 3, then show that A square plus B square is equals to 9. Okay, so solution here, W is equals to A plus IB and W plus 6 is equal to 2W plus 3, then show that A square plus B square is equals to 9. So in here what we will do, W plus 6 is equals to modulus W plus 6 is equals to modulus W plus 2W plus 3. So W value it is given, so I will put it in here. A plus IB plus 6 is equals to 2A plus IB plus 3. So this I can write as A plus 6 plus IB is equals to twice A plus twice IB plus 3. So this becomes A plus 6 plus IB is equals to twice A plus 3 plus twice IB. Root over this becomes A plus 6 the whole square plus B square This becomes twice a plus 3 the whole square plus 2b the whole square. So squaring both sides, I will get a plus 6 the whole square plus b square is equals to 2a plus 3 the whole square plus 4b square. This is a square plus 6 square plus 2 into a into 6 plus b square, 2a the whole square plus 3 square plus 2a dot 3 plus 4b square. So this is a square 36 plus 12a plus b square, 4a square plus 9, 3 to the 6, 6 to the 12a plus 4b square. So now in here you see this and this, I can cut it. Everything I will bring it to left hand side. So I will get a square minus 4a square plus 36 minus 9 plus b square minus 4b square is equals to 0. This becomes minus 3a square plus 36 minus 9. This becomes 1, 2, 3, 4, 5, 6, 7. 27 minus 3b square is equals to 0. I will take minus 3 common. I will take a square minus 9 plus b square is equals to 0. So a square minus 9 plus b square is equals to 0. A square plus b square is equals to 9. So this is I have to solve, that is I solved it. Okay. In here you can write squaring both side. Okay, squaring both side I will get this, or you can show in here one step you can add a plus b the whole square plus b square is equals to root over 2a plus 3 the whole square plus twice b square the whole square the whole square. One step you can add it in here. Okay, squaring both side I will get this step. Okay. Next, question number 7. If z bar is equals to minus z, where z not equals to 0, then show that z is a purely imaginary number. So in here, question number 7, it is saying that if z bar is equals to minus z and z not equals to 0, I have to show that z is a purely imaginary number. So in here solution, first of all I will take let z is equals to a plus ib, therefore z bar a minus ib I will get. Now since z bar is equals to minus z, this is our given, so therefore I can say that a minus ib is equals to minus a plus ib. So this gives me a minus ib is equal to minus a minus ib. Everything let's bring to the left hand side. I will get a plus a minus ib plus ib is equals to 0. So I will get twice a is equals to 0. So a is equal to 0 I got. So in the complex number a plus ib, the real part became 0. Understand? So therefore I can write z is equals to 0 plus ib, because a value 0 I got. Understand? Real part became 0. In the complex number a plus ib, the real part became 0. So z will be what? Z will be is equal to 0 plus ib, which is equals to ib. So therefore I can say that z is a purely imaginary. Z is a purely imaginary number. Understand? The real part is 0, so z will be a purely imaginary number. Question number 8, number A. If modulus z1 is equals to modulus z2 is equals to 1, then prove that modulus z1 plus z2 is equals to modulus 1 by z1 plus 1 by z2. So solution, we know that modulus z square, it is equals to z into modulus z So therefore I can say that modulus z1 square, this is equals to z1 into z1 bar. Okay, this one we know, modulus z square, it is equals to z into z bar. So therefore I can write modulus z1 square, it will be is equals to z1 into z1 bar. So now you see z1, modulus z1 is equals to modulus z2 is equals to 1 given. Since modulus z1 is equals to 1, therefore modulus z1 square, this will be equals to 1. So therefore I can write this one, modulus z1 square, this is 1. So therefore this one I can write as z1 into z1 bar, this is equals to 1. Okay, so now z1 bar, this will be is equals to 1 by z1, and similarly I can say that z2 bar, this is equals to 1 by z2. Now I will start from RHS. RHS equals to 1 by z1 plus 1 by z2. So this I will get modulus z1 bar plus z2 bar. So this one I can write it as z1 plus z2 bar, okay, modulus z1 plus z2 bar. So this is equals to our modulus z1 plus z2, which is equals to LHS. Okay, so first of all, you see, first of all this I know, modulus z the whole modulus z square, this is equals to z into z bar. So therefore modulus z1 square, it will be is equal to z1 into z1 bar, and since z1 modulus z1 equals to 1 given, so therefore modulus z1 square, this will be equals to 1. So therefore since modulus z1 square, this is 1, so therefore I can write z1 into z1 bar, this is equals to 1. So z1 bar equals to 1 by z1, and similarly z2 bar is equals to 1 by z2. So I will take RHS 1 by z1 plus 1 by modulus 1 by z1 plus 1 by z2, and 1 by z1, it is z1 bar plus z2 bar, and this one I can write it as z1 plus z2, the z1 plus z2 bar, okay, and this becomes modulus z1 plus z2, which is equals to LHS. Question number 10. If z not equals to 1 is a complex number such that z minus 1 by z plus 1 is a purely imaginary number, then show that modulus z is equals to 1. So in here you see question number 10. If z not equals to 1 is a complex number such that z minus 1 by z plus 1 is a purely imaginary number, then show that modulus z, it is equals to 1. Solution. So in here, first of all, I will take let z is equals to x plus iy. Okay, in here it is saying such that z minus 1 by z plus 1 is a purely imaginary number. Okay, so this is z minus 1 by z plus 1, so is equals to x plus iy minus 1 by x plus iy plus 1. This one is equals to, I can write it as x minus 1 plus iy by x plus 1 plus iy. Now I will do x minus 1 plus iy, okay, and then x plus 1 plus iy, both numerator and denominator I will multiply it by x plus 1 minus iy, x plus 1 minus iy, okay. So this one, it will give me, let me write it in here, is equals to, this one it will give me, this one I will multiply to, and this will be a plus b into a minus b formula, and this one I will multiply to, so I will get x minus 1 into x minus 1 x plus 1 minus iy plus iy x plus 1 minus iy by x plus 1 the whole square minus iy the whole square I will get. Understand? Minus iy the whole square I will get. Okay. So this one I will multiply it, x minus y into x plus 1 minus x minus y into iy plus iy into x plus 1 minus this, it will become iy the whole square. So this one it will become x square plus 1 plus 2x minus I square y square. This becomes x square minus 1, and this becomes minus xiy plus iy plus xiy plus iy, and this becomes plus y square. Okay, by this becomes x square plus 1 plus 2x plus y square. So this one, you see, this and this I can cut. So ultimately I will get x square plus y square plus 2iy minus 1 by x square plus y square plus 2x plus 1. Okay. So now in here you see real part and imaginary part, I will separate it. Understand? This thing again I will write it in this way. This thing again I will write it is equals to, I will write it x square plus y square minus 1 plus 2iy by x square plus y square plus 1 plus 2x. Now real part and imaginary part I will separate do. So this one I will get x square plus y square minus 1 by x square plus y square plus 2x plus 1 2x plus 1 plus I 2y by x square plus y square plus 2x plus 1. Okay. So now it is saying such that this is purely imaginary number. Understand? This thing is, it is purely imaginary number. So therefore the real part will become 0. I can write, since z minus 1 by z plus 1 is purely imaginary number, therefore x square plus y square minus 1 by x square plus y square plus 2x plus 1, this will be equals to 0. So therefore in here, this whole thing, if I send it that side, I will get x square plus y square minus 1 is equal to 0. So x square plus y square is equals to 1. So that only you have to prove here. Then show that modulus z is equals to 1, or show that x square plus y square equals to 1. Understand? Modulus z is equals to 1, or show that x square plus y square equals to 1. So that one only I showed. Understand? Since this is a purely imaginary number, so its real part will become 0. This one I can write is equal to 0. So this one, if I send that side, then it will become 0 only. So x square plus y square minus 1 is equal to 0. X square plus y square is equals to 1. So next here, question number 11. If z1 is equals to 4 minus 3i and z2 is equals to 2 plus I, then verify the following. These are I have to verify here. Okay, so question number 11. Z1 is equals to given 4 minus 3i. Okay, Z1 is equals to, it is given 4 minus 3i, it is given. Okay, and Z2, it is given 2 plus I, it is given. Okay, so I have to verify that Z1 Z2, this is equals to modulus Z1 Z2. I have to verify it. Okay, so in here, so first of all, I will take modulus of z. You see, z1 is equals to 4 minus 3i. So modulus of z1, this will be is equals to root over 4 square plus minus 3 the whole square. This one you will get 16 plus 9, 25, which you will get 5. And z2 is equals to 2 plus I. So modulus of z2, you will get 2 square plus 1 square, 4 plus 1, root 5 you will get. Okay. So modulus z1 you got, modulus z2 you got. Now we will find out z1 into z2, which will be 4 minus 3i into 2 plus I, 4, 2 plus I minus 3i, 2 plus I, 4 to the 8 plus 4i minus 6i minus 3i square. So 8 minus 2i plus 3. So this it will become 9, 10, 11. 11 minus 2i. So therefore modulus z1, z2, this one you will get root over 11 square plus minus 2 the whole square. This will be 121 plus 4. So root over 125. Sorry, in here one thing I did not found. You see, this two product I did not found. Modulus z1 into modulus z2. This one you will get 5 root 5 you will get. Understand? This one you give one equation, you give equation 1. And this one you see, modulus z1 z2 you got root over 125, which one it is 5 root 5. This is equation 2. So from equation 1 and 2 you see 5 root 5, and this is also 5 root 5. From equation 1 and 2, from 1 and 2 you can say that modulus z1 z2, it is equals to modulus z1 into modulus z2. This is verified. Understand? First of all, you will take z1 is equal to this one. Therefore modulus z1, it will become root over 4 square plus minus 3 the whole square, which one you will get 5. And then z2 is equal to this one. So modulus z2 you will get root over 2 square plus 1 square, which one you will get ultimately root 5. So z1 into z2 if you do, you will get 5 root 5. This will be your equation 1. And then z1 into z2 you do, this one you will get 11 minus 2i. So modulus z1 z2 is equals to root over 11 square plus minus 2 the whole square, which is ultimately root over 125 will get, which is equals to 5 root 5. This is your equation 2. So from equation 1 and 2 you can say that modulus z1 z2 it is equals to modulus z1 into modulus z2. This is our verified. So question number 11, 2 and 3 you try to do by yourself. We will do number 4. Question number 11, number 4, you say modulus z1 plus z2 square plus modulus z1 minus z2 square. This is equals to 2 modulus z1 square plus modulus z2 square. So this is solution. Z1 is equals to 4 minus 3i and Z2 is equals to 2 plus I. Okay, Z2 2 plus I. So I will start modulus Z1 plus Z2. This it will become modulus 4 minus 3i plus 2 plus I. So this is 6 minus 2i. So is equals to this one I can write 6 square plus minus 2 the whole square. So this will be 36 plus 4. This will be root over 40. Okay, so therefore z1 plus z2 square, this will be 40 the whole square. So modulus z1 plus z2 square, this will be 40. Understand? Next I will do modulus z1 minus z2 I will do. So this one is equals to modulus 4 minus 3i minus 2 plus I. So this one 4 minus 3i minus 2 minus I. This one 2 minus 4i. This is equals to root over 2 square plus minus 4 the whole square. This one 4 plus 16. This one root 20. So therefore z1 minus z2 square root 20 the whole square. So z1 minus z2 square, this one you will get 20. Okay, so therefore modulus z1 plus z2 square plus z1 minus z2 square, this will be 40 plus 20, which will be equal to 60. Okay, now I will start from this one I will start. Okay, so now it is, you see, z1 is equals to 4 minus 3i. So modulus z1, this will be equals to root over 4 square plus minus 3 the whole square. This will be 16 plus 9. This will be 25. This will be 5. Okay, so therefore modulus z1 square, this will be 25. Then similarly next z2 is equals to 2 plus I. So modulus z2, this will be equals to root over 2 square plus 1 square. 4 plus 1 is equals to root 5. So therefore modulus z2 square, this will be 5. Okay, so therefore z1 square plus modulus z2 square, this will be 25 plus 5 is equals to 30. I will get. I will multiply 2 both side. Modulus z1 square plus modulus z2 square is equals to 30 into 2, which is equals to 60. I will get. This is equation 2 you give, and this one equation 1 you give. Understand? So from equation 1 and from equation 2, what I got? That this is equal to this I got, because both side only 60 I got. So therefore from equation 1 and 2, from equation 1 and 2, I can say that modulus z1 plus z2 square plus modulus z1 minus z2 square. This is 2 z1 square plus modulus z2 square. This is our verified. Understand? So similarly, rest of the problems you can do. Okay, similarly like this, rest of the problems you can do. Next I will go to question number 12. If you have got any difficulty, anything you have not understand, you please write it in the comment section. I will try to clear your doubts in the next video. So now it is question number 12. It is saying that prove that, question number 12 saying that prove that modulus z square, it is equals to modulus z the whole square. Okay, so now I will take let z is equals to x plus iy. So z square will be x plus iy the whole square, which will be is equals to x square plus iy the whole square plus 2x iy. This is x square minus y square plus 2x iy. So modulus this, it will be modulus x square minus y square plus 2x iy. So this is equals to root over x square minus y square the whole square plus 2xy the whole square. This is equals to x square the whole square plus y square the whole square minus 2x square y square plus 4x square y square. This is I will get x square the whole square y square the whole square minus 2x square y square I will get. Understand? So this one is equals to I will get root over x square minus y square the whole square, which is x square minus y square. Understand? Which is x square minus y square. This is equation 1. And next I will do this one. So modulus z, this will be is equals to root over x square plus y square. So therefore modulus z the whole square, this one you will get, oh sorry, here I did a mistake, this will be plus, so plus, okay, understand, this will be plus, so square, this will be x square plus y square the whole square. So therefore modulus z square is equals to x square plus y square. This is equation 2. So from equation 1 and from equation 2, from equation 1 and 2, what I can say, that this is equals to this, it is proved. Understand? So like that we can do. If you have any doubt or any problem, you please write it in the comment section. Okay. Next it is 12 number B, saying that for any complex number z, if this is equals to this, then show that Rez is equals to, that means real part of this complex number is 0. Rez means real part of this complex number is 0. Real part of z is 0. So in here solution I will take, let z is equals to x plus iy. Okay. So this is our given modulus z plus 1, it is equals to modulus z minus 1. Put the value of z here, plus 1, x plus iy minus 1. So this is, I can write x plus 1 plus iy, this is equals to x minus 1 plus iy. So this becomes root over x plus 1 the whole square plus y square is equals to root over x minus 1 the whole square by y square. So this one squaring both sides, I will get x plus 1 the whole square plus y square is equals to x minus 1 the whole square plus y square. If I break it into formula, x plus y, re is equals to real part of z is equals to 0. I have to solve. Okay, so if I break this, and this is x square plus 1 square plus 2x plus y square, this will be is equals to x square plus 1 square minus 2x plus y square. So this whole thing we will bring, left hand side we will bring, I'm showing you in here. So this one I will get x square plus 1 plus 2x plus y square minus x square minus 1 plus 2x minus y square is equals to 0. I will get. Understand? So this one and this one I can cut it, and then 1 1 minus 1 minus 1 I can cut it. I will get 2x is equals to 0. So x is equals to 0. Understand? So what I should, x is equals to 0 I should. This complex number is what? This complex number is x plus iy. Understand? And in here what I showed, x is equals to 0 I showed. Real part of the complex number I showed 0. That one only I have to show here. Rez is equals to 0 I have to show here. So therefore I can directly say that Rez is equals to 0. This is shown. Understand? If you have got any doubt, you please write it in the comment section.